Hi, welcome to Alien Space Education. My name's Andy. I'm your host for this amazing episode all about the dynamics of our sun, the most crucial star that we know is important to us. So we're looking at how we are turning our gaze. We're turning our gaze towards the sun, the heart of our solar system, also known as Sol. The sun is so much more than just a bright ball of light in the sky, and it's not white. It's yellow that you see, depending on, or red, depending on where you see it in the sky. It's a white ball that's going like that. It's a medium mass star, and it governs everything in our solar system, from the smallest asteroids to the largest planets. And even life on Earth is influenced by the sun. So over this entire episode, we'll dive into the sun's structure, its life cycle, and its profound impact on our planet. I really hope you enjoy. Please like and share, and let's get into it. So we start off with Sol, the sun's place in our universe. So let's start by understanding the sun's place in the universe. The sun is a star. It is one of an estimated 100 billion stars in the Milky Way. It's classified as a G-type main sequence star or a G-dwarf star, which means it's a medium-sized star in the prime of its life. It's about 4.6 billion years old. We can't say exactly to the date, as we don't know, but 4.6 billion years old, and it's roughly halfway through its life cycle, with it another 5 billion years to go before it exhausts its nuclear fuel in the centre. So we've got to wait 5 billion years before it grows any bigger. So we're perfectly safe. It's going to go well and it's going to look after us. The terms of size, the sun is immense. Its diameter is about 1.4 billion kilometers, or 870,000 miles, which is roughly 109 times the diameter of Earth. So you have to have 109 going directly across from one side of the sun to the other. 109 Earths lined up next to each other. In terms of the mass, the sun accounts for 99.86% of the total mass of the entire solar system. So that's 99.86. The other 14% is all the planets, all the asteroids, everything else. Your cloud is all the remainder of 14%. The rest of it is all the sun. So, in comparison, the planets, the Earth, everything else, all the moons, make up a tiny fraction of mass compared to the sun. If we put us on scales, the sun would outweigh us massively. This immense mass is what allows the sun to exert such a powerful gravitational influence of holding our solar system together. If the sun was bigger, the solar system would be very different. If the sun was smaller, the solar system would be different. But because it's just right, our solar system holds together really, really nicely. But what sets our sun apart from the other stars in its proximity to Earth? It's about 150 million kilometers, or 93 million miles away from us. This distance is known as an astronomical unit, or AU. If you've watched my other episodes, you may have heard me use that. So there it is again. This serves as a standard measure of distance within our solar system. So despite its vast distance, light from the sun takes about 8 minutes and 20 seconds to reach Earth. Travelling at the speed of light about 300,000 kilometers per second, or 186,000 miles per second. So it's travelling at super fast speed, but it still takes us 8 minutes and 20 seconds to see that. So if we're looking at the sun, if you can look at the sun safely, wear the right glasses, make sure you're protected. If you look at the sun, you're looking at 8.5 minutes in the past. You're looking back in time because it takes that long for you to see it. That is really cool. So we're talking about time travel now. Wow, that's good. Well, a little bit anyway. So, what do we know about the sun, the structure of the sun? Now that we have a sense of the size of the sun, we know it's massive. We know how big it is. Let's dive into the structure. The sun is made up of several layers, not just one layer. It's not just one big ball. It's got layers, just like Earth has layers of crust, the core, and everything in between. The sun has a very similar thing, each with its own unique properties, just like Earth. For the innermost core and the outermost corona, these layers work together to produce energy and light that we see. So it's happening right at the innermost core. At the heart of the sun is the core. When nuclear fusion occurs, the core has a temperature of about it's only 15 million degrees. You'd only get a slight sunburn from it. No, it's really, really hot. Or 27 million degrees Fahrenheit. 15 million degrees C or 27 million degrees Fahrenheit. That's really, really hot. Really hot. You get more than a sunburn, trust me. Here is where hydrogen atoms are fused together into helium, releasing enormous amounts of energy in the process. In this process, the energy is what powers the sun, and the process, the light and heat, and processes the light and the heat that reaches us eventually. So without this fusion going on, this light wouldn't be there. The core is incredibly dense, incredibly hard, and contains about half of the sun's mass in just about 2% of its volume. You think of how big it is, 2% of that is where all this light and heat is coming from. Just 2%, tiny little bit in the middle. Surrounding the core is what is known as the radioactive zone. This is where energy from the core is transferred outwards by radiation. In this zone, photons of light are absorbed and re-emitted countless times, taking hundreds and thousands of years to move through this layer. It takes a long time to get through this layer because it's bouncing around. The radioactive zone extends to the edge of the core to about 70 way through the sun's surface. 70% of the way from the core to the edge. It's not all the way there yet. We've still got 30% left to go. Well, 28%. 28% left to get to the surface. And we're still talking hundreds of thousands of years for that light that's in the centre of the sun to pass through this radioactive zone to get out to us. So the sun we feel, the light we feel, is thousands of years old. Beyond the radioactive zone, there's another zone, and this is called the connective zone. This is where the energy is transferred by convection. In this layer, hot plasma rises up to the surface, just like magma rises up to the surface of Earth. Rises up to the surface, cools down, and then sinks back down to reheat, creating a convective current. This movement is similar to the way boiling water circulates in a pot. It bubbles up and sinks back down. It bubbles up and sinks back down. It's very, very similar. This connective zone is responsible for the sun's gradual appearance with a surface covered in bright bubbling cells called granules. So we're looking at the granules. It's all bubbling and everything like that. It's all happening in this convective zone. And it's happening. And that's what makes it look like it's boiling and everything like that. And then we've got another layer, the outermost layer. This is getting bigger. This is the layer of the sun we can see. So these first three, we can't even see them. It's all bubbling underneath. But the bit we see, just like the Earth, it's the crust of the surface. We don't see the magma underneath. We only see it when it bursts through. But that's underneath everything. So the outermost layer, this is the bit we see, called the photosphere. The photosphere is where the sunlight is emitted after taking thousands of years to come through, and it's perceived as the sun's surface. Even though it's not solid surface like Earth, its temperature on the outer edge, remember it's 15 million degrees middle, the outer edge is around 5,000 degrees C or 9,932 degrees Fahrenheit. This photosphere is still incredibly hot. Photosphere is also relatively thin, like the crust of the Earth is relatively thin compared to the rest of the Earth. It is really, really thin. Think of a core of an apple. Everything's happening underneath, but the skin of the apple is very, very thin. Same thing, Earth, Sun, apples, all the same. They all have different layers. Okay, the photosphere is very thin, even though it's only a few hundred kilometers thick. So it's a few hundred kilometers thick, and it's this layer where sunspots, cooler and darker regions are caused by the magnetic activity which are visible to us, and we can monitor that, and we are monitoring that. That's when we know there's things happening underneath. And the more the convective zone, this bubbling effect affects the photosphere, and we see that. Above the photosphere, there's another layer. Oh my God, there's more! And this is the chromosphere. It's a thin layer that is visible during the solar eclipse as a reddish ring around the sun. So we need a solar eclipse to see it. Okay, the temperature of the chromosphere increases with height to reach up to 20,000 degrees Celsius or 36 degrees Fahrenheit. So even though the photosphere is about 5,500 degrees, this chromosphere is so much hotter on the outside. It heats up. The photosphere is heating up the chromosphere. The chromosphere is now 20,000 degrees hot. So it's changing temperature all the time, hence why it's always looking differently and everything like that. And finally, on top of all that, we have the corona, the sun's most outer atmosphere. The corona is incredibly hot, diffuse region with temperatures soaring in millions of degrees in Celsius. The corona extends millions of kilometers into space and is best observed during a total eclipse with specialized equipment called coronagraphs. Now, if you talk to your school or whoever, they will know about these and they will help you guide them. I will see what I can do to give you more information, but I don't have one with me. Okay. The corona is a source of solar winds and a stream of charged particles that flow outward from the sun that interacts with planets in our solar system. We see that as solar auroras. We see that at night, we see auroras and everything like that. So the corona is where we have a probe at the minute that touches the edge of the sun and it's touching the chromosphere. That's how close we can get. When we say we touch that, we're touching the corona. I wonder how many of you put it, write in the comments below if you're watching this on YouTube or whatever, or email me. Tell me what that probe is called. I'd love to see how many of you guys know that. Okay, so just like us, just like anything else, it has different layers, and what happens in those layers is very different. Okay, now what about the sun's energy and this nuclear fusion that's making it work? Because we now looked at the different structure, now we talk about the engine that powers it, nuclear fusion. The sun's energy comes from a fusion of hydrogen atoms in its tiny little 2% core. It's under extreme pressure and temperature in the core. Nuclei, which are protons, collide and fuse together to form helium nuclei. This process releases a tremendous amount of energy in the form of gamma rays. Don't worry, you're not going to turn into the Hulk. Those who like Marvel will understand that. But that's where it all happens, right at the very start and centre. But how does the fusion actually work? It comes down to the conditions in the sun's core. The core's temperature and the pressure is so high that they overcome electrostatic repulsion between the positive and charged neutrons. When the two protons get close enough A strong nuclear force which binds nuclear atoms together, takes over and fuses them into a singular nucleus. This process releases energy according to Einstein's equation, E equals mc squared, which states that mass can be converted into energy. Pushing these tiny nucleuses together billions and trillions of times per second in the center of the sun, and then this takes thousands of years to come through the sun, and then it gets hotter and eventually reaches us. Shows us how incredible the sun is and how much heat it produces. The fusion process in the sun, it primarily follows what's known as proton-proton chain reaction. This reaction, 4 hydrogen nuclei, protons, are eventually converted into one helium nucleus, with some mass being lost in the process. As some mass is lost, this lossless mass is converted into energy, which radiates out from the core through radioactive and through the radioactive and conversion zones, eventually reaching the photosphere and escaping into space as sunlight. That's where the sunlight starts. That's the process. It starts way down, right down in the middle of the sun, and it can take thousands, hundreds of thousands of years for that sunlight to reach us. So the sunlight we're feeling is thousands of years old. That's taken a long time to get here. The energy produced by nuclear fusion, which makes life possible on Earth. Without the sun energy, our planet would be frozen, lifeless. We wouldn't be here. It'd be a cold rock, the water wouldn't flow, nothing would happen. The sun's energy drives the water cycles, powers photosynthesis in plants, warms the Earth's surface, creating the conditions necessary for us to live. So without the sun, we wouldn't be here. Plants wouldn't be here. Nothing would be here. So the sun is crucial to us, and it's important that we understand that. That's a lot, isn't it? Oh, good God. Now, let's breathe for a second. Taking a few rays of sunlight, take a big deep breath. Now, if you listen to my last episode, The Life Cycles of Stars, we're going to very quickly go over the sun's life cycle. Now, remember, the sun is a medium mass star. Okay, so our sun is currently in the middle of its life. It hasn't always been stable. Shining stars we see today, it won't remain so forever. It will eventually change. It has a life cycle which begins billions of years ago, and continues for billions of years more. Remember, these are billions of years, not millions, not centuries, not thousands. We're talking billions. Billions of years, okay? The sun was born about 4.6 billion years ago from a cloud of gas and dust. This cloud, known as a solar nebula, began to collapse under its own gravity, forming a protostar at the center. As a protostar grew in mass, its temperature and pressure increased under nuclear fusion, igniting it in its core, making the birth of the sun. 4.6 billion years ago is when this process started. Currently, the sun is in the main sequence phase. If you want to know more detail about this, please go back and listen to my other podcast. Alright, so we're in the main sequence phase. It's been there for the past 4.6 billion years. During this phase, the sun steadily converts hydrogen into helium in the above process that I just mentioned in its core, producing energy and maintaining a stable size and brightness. Which means because it's stable, it's not changing shape so much or anything like that. It's stable, it's fine, nothing bad's going to happen. However, the main sequence won't last forever. Nothing ever does. Just like us, it grows old, and after about 5 billion years, the sun will exhaust its hydrogen fuel. It won't be able to eat any more hydrogen because it won't have any more. When that happens, the core will contract, heat up, with the outer layers expand and the sun will enter the next phase of its life as a red giant. It's going to grow bigger, stronger, more powerful as a red giant. As a red giant, the sun will grow to a normal size, possibly engulfing the inner planets of the solar system, including Earth. So that means if you look at the map of the solar system, flat on the left, you see Mercury, Venus, Earth, and Mars. When the sun becomes a red giant, it could expand to the edge or even eat Mars. It will grow that big, round, so it will go all directions, up, down, left, right. It will go about up to Mars. We think it might go bigger. We don't actually know how big it will go, but it could eat all 4 planets, including Earth, because Mars is after Earth. So it's going to go really, really big. So once it's done that, the core is now hot enough to fuse helium into heavier elements like carbon and oxygen. So just like the sun had started to convert hydrogen into helium, now it's converting helium into other elements like carbon and oxygen. And as it converts these, it will continue to shrink, while the outer layers, and once it's eaten that, it will shrink. It will eject its outer layers into space like a big, beautiful cloud, like a firework, and create a brand new planetary nebula. Eventually, the sun's core will no longer be able to sustain fusion. It will shed its outer layer, leaving a hot, dense core known as a white dwarf at the center. This white dwarf will gradually cool, fade over billions of years, ultimately becoming cold, dark remnant, a black dwarf star. But that's so far in the future, it's almost impossible to imagine. So that's how far we're going. We're going so far away, we can't even see it. It's too far away for us. Oh, that's a long way away. But when we look at a black dwarf star up in the sky, it can be miscommunicated as a rogue planet because it's just a black ball floating around. So we're still trying to isolate what each one is. We're working on it. Okay, going on. Solar activity and space weather. Now, just like the Earth, we have wind patterns, rain patterns, clouds, snow, sunshine, depending on what's happening. So we have to monitor the sun and the sun's activity on the surface. So while the sun's long-term life cycle is fascinating, its short-term behavior is just as intriguing. So we look at both the long and short. The sun is not a static object. The surface is always changing. It's incredibly dynamic with constant shifting magnetic fields, solar flares, eruptions that can have a direct effect on the Earth. Could these be? Well, let's go through it. The sun's magnetic field is responsible for so much activity. The field generated by the movement of charged particles within the sun, in particular the convection zone. The sun's magnetic field is complex and constantly changing, with these magnetic lines twisting and tangling as the sun rotates and convects. So it's always moving, it's always changing, and it's happening right now below the surface. And it's having a massive effect on everything. One of the most visible manifestations of the sun's magnetic activity is sunspots. Nice and easy. My apologies, something happened there, so we're just going back over where we were. So one of the most visible manifestations of the sun's magnetic activity is sunspots. Suns are dark, cool areas on surfaces caused by contractions of the magnetic field lines. These spots often associated with solar flares or coronal mass ejection, CMEs. If you're into space, you'll understand what they are. You'll know about them, and I'll cover them later on. Powerful bursts of energy and plasma that can erupt from the sun's surface. These are magnificently powerful, magnificently beautiful. You need specialist equipment to monitor them, but solar spots, if you've got a good telescope and you can attach a camera to it and look through a camera, don't look directly at the sun through a telescope. Use a camera, use a different means, protect your eyes, and you can see some changes on the surface of the sun. Solar flares are intense bursts of radiation that occurs when magnetic energy build up in the sun's atmosphere is suddenly released. These flares can emit radiation across its electromagnetic spectrum in the form of radio waves to gamma rays. When solar flares are particularly strong, they can cause disturbances in the Earth's ionosphere, affecting radio communication and even causing temporary blackouts to GPS signals. So the sun, even though it's thousands, millions of miles away, it can still affect our GPS. Wow. That's magnificently powerful and really, really cool. So that's why we have to monitor the weather, because Elon Musk launched some SpaceX satellites for his internet, and because he put them in a low Earth orbit that he was meant to do, the solar flare actually pushed them lower and he lost them all. So he just launched them up and he lost all 20 of them. Not good, but it happens. So he had to launch them more. So he learned from that. It happens. So we have to monitor the weather to make sure we protect our satellites. The coronal mass ejections, or CMEs, are another form of solar activities. These massive bursts of solar winds and magnetic fields rise above the solar corona and being released in space. When a CME is directed towards Earth, it can interact with our planet's magnetic fields, causing a geomagnetic storm. These storms cause disturbance to satellites, power grids, but can also create beautiful auroras at the polar regions. So even though the sun can create destruction, it can help support life, it can really affect our power grids and some of our satellites. So we have to monitor them carefully. We have to check everything. We have to know what's happening, because remember, it takes 8 minutes and 20 seconds for it to reach us. And we need to prepare and we need to move quickly. We have 8.5 minutes to protect ourselves. So we've got to constantly monitor it. The sun's activities follow an 11-year cycle, give or take, known as a solar cycle, during which a number of sunspots, flares, and CMEs increase and decrease. We currently, since records began in solar cycle 25, which is expected to peak next year in 2025, or this year, depending on when you listen to it, which is increased solar activity. So we're expecting a lot of CMEs, solar flares, and other things to happen, and we're going to monitor it and see what happens, and we're going to be safe. So keep an eye on your electrical systems, keep an eye on any blackouts you may get or anything like that, because it might not be down to computer failures or things like that. It could be down to the sun that causes problems. Think about it. So it's really going to be really cool what happens. Now, the sun's influence on Earth and beyond. Well, we know the sunlight takes a long time to reach us, but what happens further afield? The sun's influence extends far beyond just providing light and heat to Earth. Its energy drives the climate, influences the weather, and even shapes the environment of space around our planet. It's constantly affecting us in many ways. The sun's energy output and solar irradiance is the primary driver of Earth's climate. Changes in the solar rhythms, even small ones, can have significant effects on Earth's climate over time. For instance, during the Maunder Minimum, a period of low solar activity in the 17th century, Europe experienced what is often referred to as the Little Ice Age, with colder than average temperatures. But that was back in the 17th century. We haven't experienced that since. But the sun's influence isn't just confined to Earth. Solar winds continue to stream of charged particles released from the sun's corona, shapes the environment of the entire solar system. This wind interacts with magnetic fields of planets, creating phenomena like Earth's magnet, which protects us from harmful cosmic rays. We see the aurora lights. We see what's going on when the sun rays hit us. But we've also noticed it on Jupiter, Saturn, and other planets. So these rays that we see it hitting other planets and everything like that. So it's really cool that we're not the only ones being affected. In space, solar winds will also sculpt the tails of comets, blowing them away from the sun, and affects the orbits and atmosphere of other planets. So the sun is affecting everything. Solar winds affect everything. The sun's heliosphere bubble of solar winds that extends far beyond the orbit of Pluto marks a boundary of a system where the sun's influence wanes and the interstellar space begins. So, if you've listened to any of my old podcasts from season 1, you'll hear about the Oort cloud. And there's comets, rocks, and all sorts of things in the Oort cloud that expands for a really long region. But that's the edge of our solar system. It's beyond Pluto, 2,000 light years to 100,000 light years away. And this, 2,000 AU to 100,000 AU, sorry. The sun is affecting these rocks out there in the Kuiper Belt and beyond. It's all cloud. But it's still affecting all these out there right on the very far edges, so the sun is having a greater gravitational pull than we realise. However, when these go further afield and go to the edge of the Oort cloud at 100,000 AU away, what happens when it turns back? What forces it? What swings it back? Why? Because if it keeps going away from the sun and the gravity's not there, the sun's not having an influence, it'll just keep going. But something pulls it back. So the sun is incredibly powerful in making this happen, which is really, really, really cool. The sun has also had a central figure in human culture. And we're going to have a little look at that. Human culture and science. The sun has been the central figure in all of it. For thousands of years, it's been worshipped as God. Uses to mark time, and we also studied to unlock the secrets of the universe. Ancient cultures, the sun often defied and worshipped as a powerful entity. Egyptian revered Ra, the sun god, as a ruler of the heavens. The Inca worshipped Inti, the sun god, who was believed to be the ancestor of their rulers. Many other cultures, such as ants from the Aztecs, also have solar deities. So the sun has influenced every religion, every culture in one way or another. The sun has also played a crucial role in the development of science. Early astronomers, such as Aristarchus or Copernicus, studied the sun's movement and developed a heliocentric model of the solar system, which placed the sun at the centre of the solar system rather than the Earth, which they used to believe the Earth was the centre, but then they discovered the sun was, which was a revolutionary idea that changed our understanding of the universe and our place in it, to change where we are in the universe. No, we're the central. We're not. The sun is the centre of the solar system, and everything revolves around the sun, not everything revolves around us. In more recent times, the study of the sun has led us to breakthroughs in physics, in particular the understanding of nuclear fusion, magnetism, and space weather. Observatories and space missions like the Spark Solar Probe and the Solar and Helios Observation (SOHO for short) have provided invaluable data that helps us understand the sun's behavior and the impact on the solar system. Not just us, they're looking at the wider field. So the sun is incredibly important, incredibly has a lot of stuff we're learning about it. It's been worshipped as a god, it's changed our way of looking at science, and we're still learning about it today. The sun is immensely cool. And you think all stars, which are the sun is a star, go through similar cycles for different lengths of time. They may have other rocks, other planets around them, and they could be worshipped. We just haven't met them or communicated with them. We have so much to learn, so much to understand about the sun and everything. It's going to be amazing. From its violent eruptions to its gentle warming rays, the sun is a reminder of the incredible power, beauty of the universe. As we continue to study this star, our star, we uncover more about its nature, its history, and its future, gaining a deeper appreciation for the role it plays in our lives and all lives on this planet, human or animal or nature. It affects everything. Thank you for joining me on this amazing episode about the sun. I really hope you enjoyed it. I really hope it's made you think a little bit about the sun and how it affects your lives and what we've learned from it and what we're going to learn from it in the future and how we can use it in the future for space travel. Because that's ultimately why we're learning, so we can see how all changes. Please like, share, enjoy. I look forward to seeing your comments and everything else. Keep looking up to the stars. And if you have any questions, please get in touch. Look to the skies. Take care.